In today's video, we are going to learn about magnets and, more specifically, how we represent magnetic fields using field lines. A magnet is any kind of material or object that generates a magnetic field around itself. The most familiar type of magnet you may have seen is a bar magnet, which is a simple, rectangular magnet with clearly defined poles. However, magnets actually come in a wide range of shapes and sizes, from small and curved horseshoe magnets to something as enormous as the planet Earth itself, which functions like one massive magnet. Regardless of their size or shape, all magnets share a common characteristic. They always have two poles, one called the North Pole and the other called the South Pole. These magnets are surrounded by an invisible region of influence, known as the magnetic field. To illustrate or visualize this magnetic field, we use a helpful tool called field lines. These field lines are essentially drawn as arrows that begin at the magnet's North Pole and extend outward and curve around, ending at the South Pole. It's important to know how to correctly draw these field lines, especially if you're preparing for an exam, and to ensure all the arrows are pointing in the proper direction from north to south. The simplest method to draw these is to first sketch a straight line that exits from the North Pole and enters the South Pole. Then you can add a pair of curved lines doing the same, one on each side, coming out of the North Pole and curving into the South Pole. Finally, complete the diagram by drawing larger loops that extend all the way around from the north to the south, mimicking the natural spread of the field. While it is possible to add more arrows following the same pattern to make your diagram more detailed, it is generally not necessary unless specifically asked. After drawing, it is crucial to review and verify that every arrow is correctly pointing out of the North Pole and into the South Pole. Using field lines to represent magnetic fields is helpful because it not only shows where the magnetic field exists and the direction it is acting in, but it also allows us to visualize the relative strength of the field in different regions. The density of these field lines, which refers to how closely spaced they are, indicates the strength of the magnetic field. Closer lines represent stronger fields, while lines that are farther apart indicate weaker fields. For instance, we can observe that the magnetic field near the North Pole is significantly stronger than the field farther away from the magnet, simply because more field lines are concentrated in that region. Although we cannot see magnetic field lines in real life, and not all magnets are conveniently labeled with North and South Poles, we can still detect and map out magnetic fields using a compass. This works because the needle in a compass is actually a tiny bar magnet itself. It naturally aligns with the magnetic field it is placed in and always points toward the South Pole of any nearby magnet. So if we place a compass near a magnet and observe the direction the needle is pointing, we can draw an arrow in that same direction, knowing that it indicates movement toward the South Pole. For example, if the compass needle points toward a specific side of a magnet, that side must be the South Pole. Conversely, if it points away from a side, then that side is the North Pole. By repeating this process at multiple points around the magnet, we can gradually build up a complete diagram of the magnetic field by joining all of the arrows to form continuous field lines, just like in our earlier illustrations. If you are curious to see this method in action, we have included a link to a live demonstration video in the description below. Lastly, we should consider what happens when two different bar magnets interact with one another. If we try to bring two North Poles together, we will notice that they repel each other, which creates a resisting force that makes it difficult to push them close. This repulsion is explained by drawing the magnetic field lines between them. The field lines clash and push away, generating a force of separation. On the other hand, if we flip one of the magnets so that a North Pole is facing a South Pole, the field lines from one magnet flow directly into the other. This configuration results in the magnets attracting each other, since the field lines naturally move from north to south, creating a pulling force. And that brings us to the end of today's video. We hope you enjoyed this explanation and found it helpful. Make sure to give us a like, subscribe to the channel, and we'll see you again in the next one.